Thank you all for coming. It's great to be here. I'm going to talk to you today a little bit about what we do at the Nevada National Security Site and who we are and what our mission space is. We're a site that is part of the U.S. Department of Energy's research enterprise. Now, it's actually, the DOE has a very large complex. It involves 17 national laboratories, and then several plants and production sites, and then our Nevada National Security Site. And so all in all, it's something like 60,000 scientists and engineers who are involved in this research enterprise. So lots of people. And so I get to come around and talk to universities because, of course, we're always looking to hire more people. Because it's a large group, we get lots of people turning over. Actually, DOE has a big problem right now in that it's very, very old. And so the estimate is something like 5 years from now, 60% of all people employed at the DOE research sites will be retirement eligible. 60%. Now, don't get me wrong, that doesn't mean they'll actually retire. People in DOE are terrible at retiring, and they mostly don't, and they work until they're very, very, very old. But obviously, when you get a lot of people getting up to be in that kind of age group, you really have to be looking for the next generation of researchers, and we need to make sure that we have people who are coming out of universities here in the United States who have the right skill set. Now, before I kind of go into any of these details here, I'll just give a little bit of a commentary on whom we hire. So in the research complex, we certainly hire people from all nationalities. So the national laboratories are not restricted to U.S. citizens. So if you want to go to work at Los Alamos National Lab, it doesn't matter where you're from. If you want to work at Livermore, Sandia, it doesn't matter where you're from. In my own organization, we actually hire U.S. citizens only. And I mean that exactly as I said, citizens. Green card holders, actually, we don't even hire in our organization. But in the complex, we hire people from all over the world. And so the application I'm going to talk about here today is actually much broader than just my organization. And if it's interesting to you, you can go do it at Los Alamos, or you can go do it at Livermore. And there are people who hire you to do that. So Mary Lisa is one of my colleagues in my group. Like was mentioned, I'm a manager of a group. I have 32 people in my organization that report to me, and they are physicists, engineers, and mathematicians. So we have only 6 PhD mathematicians in my entire company of 2,000 people. But we all work together in North Las Vegas, and because there's only 6 of us, we kind of get to do what we want. Yeah, it is some power. So the mathematicians, they view us as a very strange breed. Like nobody quite knows what we are. And so when we do weird things, like we can do whatever we want because people say, well, that's what the mathematicians do. And like we don't get in trouble then because they think, oh, just that's how mathematicians are. Now, unfortunately, the people in my group, we're all smart enough to totally game that system. So we're always trying to gauge what can we get away with just because we're mathematicians. But I want to talk about some of these other people here in this group, and actually most of this collection of people are mathematicians. But I want to talk about a couple of names here, specifically Mike and Kevin. Mike Fowler and Kevin Joyce, they are both people whose actual work from their PhD theses is in this talk. So, I mean, in some sense, I made this as sort of highlighting Mary Lisa and me because actually Mary Lisa and I literally made this talk together because she gave it at one place and I gave it somewhere else. But the material in here, very much Mike and Kevin are involved. Mike was one of our graduate student interns, and he came to us and he said, I like what I'm doing. How about if we make this my doctoral dissertation? We said, sure. So I co-advised his PhD, and then when he graduated, I was telling some of you earlier, Mike's the one who went off to MathWorks. So now he works on Simulink. I send all my complaints about MATLAB directly to him, and then he writes me and says, I don't work on MATLAB, I work on Simulink. It's too bad, I'm going to complain to you anyway. Kevin was similar, so actually I started working with Kevin's PhD advisor, and then Kevin got roped in through his advisor, but Kevin worked with me as a graduate student intern for 3 years. I funded his entire PhD, and then I hired him as a postdoc. So now he works for me as a postdoc in our group. And the other people I just want to call out by name, Jesse and Maggie, they are both graduate student interns who have worked with me for a couple of years. I am co-advising Jesse's PhD. He's graduating from the University of Arizona in 3 weeks. And Maggie is a PhD student at the University of Alabama, Huntsville, and my colleague Mary Lisa is co-advising her PhD. So this is actually really a common paradigm for us. We get in students, actually Maggie came to us as an undergrad, and now we're funding her PhD. And so we like that kind of paradigm where when we get good interns, we want to keep them with us and we help support them. So we want to help build people up who have the right skill set and the right backgrounds to work in the U.S. Department of Energy. Okay, so what is the Nevada National Security Site? Well, it's a big hunk of Nevada desert. So this chunk here in the city of Las Vegas is right there. This is about, depending on how you measure, if you measure to the gate, it's about 70 miles. And this facility is larger than the state of Rhode Island. So it's almost 1,400 square miles. So it's pretty large. And we've got roughly 20 research sites there where we do different kinds of experimentation. But historically, the reason that we needed a very large facility was because this was the place where the United States started doing atmospheric nuclear testing in the 50s. Now, the first atmospheric testing was actually in the South Pacific. It wasn't in the US. The US actually blew stuff up in the South Pacific. And then people decided, hey, that's not very nice of you guys. So we moved it back into the US and we started doing nuclear testing in Nevada. There were actually several different places that had become sort of candidates for the facility, but Nevada was the only place where you had a giant expanse of desert with basically no people. And Las Vegas existed as a city at that time, but in 1951, Las Vegas was a hick little town, right? It was not a major city. Today Las Vegas has 2 million people. In those days it had tens of thousands. It was pretty small. And so then you have this giant chunk of Nevada desert, and there was nobody living out there, and there was nobody who was ever really going to move into that part of the Nevada desert. And so it seemed like a reasonable place. Now, that went on actually until 1961, and in 1961, we actually had a moratorium on nuclear testing. So it was a joint sort of gentleman's agreement that we had with the Russians that we would stop testing altogether. And so we went a couple of years with no tests, and then in 1963, the Russians broke the agreement and they set off what is still to this day the largest thermonuclear explosion ever. And so once the Russians did that, then we said, ooh, well, we're all going back to testing now. But we did actually sign a formal treaty that we would no longer do atmospheric testing. So all the testing went underground. From 1963 until 1992, we basically set off over 800 thermonuclear weapons, just to test things. You want to know, do your weapons work? Well, we put them in the ground and we set them off, and when they went boom, we said, yep, they work. We laughed, but it was almost that simple. That was sort of our version of the scientific method in those days, which is actually, if you're a scientist, that's the version of the scientific method you want. Right? You want to know an answer to a question, and so what do? You test it. Well, in 1992, the first President Bush said, we're not going to do that anymore. So he made a unilateral decision. It was a presidential directive issuing a moratorium just for the United States on nuclear testing. There was no treaty, there was no agreement with anybody else. We simply stood down and said we will no longer do nuclear testing. In 1994, under President Clinton, it actually became a law that we do not test. Now, the law is sort of funny because, of course, like all our laws, it has some loopholes and some exceptions and things like that. But we have not actually, we have not done a nuclear test since 1992. And we actually, at the site, we have a little bit of a museum because there was a nuclear test that was supposed to go off in mid-August of 1992. And at the last minute, they didn't hit the button because they had a technical difficulty. And so their test actually got delayed about a month. And that month was exactly the month needed to issue the moratorium and not allow the test to happen at all. So what they did, though, was, and this was actually really interesting, of course they took the bomb out of the ground, but they left everything else there. So all the cables, all the measurement systems, all the diagnostics, they just walked away from it, and it's now like a living museum of what a nuclear test looked like. So I've actually been to, it's called Ice Cap, I've actually been to Ice Cap, and you just kind of walk around like, yeah, this is what people were working in those days, sort of the environment. So since 1992, since we no longer do nuclear testing, I mean, now you can imagine sort of the scientific predicament that the entire enterprise gets put into. Because President Bush, when he said we weren't going to test anymore, he said, okay, what would we need in order to ensure the safety, security, and effectiveness of the U.S. nuclear weapons stockpile if we're not going to test? So you need, you now being the scientific community in DOE, you need to be able to tell me, the President, that these weapons are safe and effective, meaning they're going to go boom the way they're supposed to go boom. And you don't get to test it. So how are you going to do that? How are you going to guarantee me that these things are going to work when you don't get to test? And what DOE came back with was, well, and I'm just using DOE broadly to mean that group of people, right? Actually, it wasn't the Department of Energy at the time. But the complex came back and said, well, if we can build gigantic computers, and we can build a couple of very large experimental facilities where we can do other kinds of tests, we think we can make this work. And what we'll do is we will drive the assessment of the stockpile by computer simulations. Now, I can't validate my codes against a true test, because I'm not allowed to do a true test, but I can design a whole bunch of other experiments that I can validate my codes against. And then we're going to make the giant philosophical leap that if my codes work on these other kinds of experiments, that my codes are telling me the right answer on the tests that I'm not allowed to do. Which is actually, to this day, that is still a great big philosophical argument that people are having all the time. If you only get to validate your codes in a regime that is not the regime you care about, how do you have confidence about your codes in the regime you do care about? So this is actually, there was a very, let's say, controversial article that was just recently published about one of these giant experimental facilities called the National Ignition Facility at Lawrence Livermore National Laboratory. And the idea behind NIF was that basically they were going to get what they call ignition. Ignition is when you do a fusion reaction that produces more energy than it took to get out, than it took to happen. And the idea was, well, we'll get NIF to work. I mean, the plan was something like 2002, I think, is when they said they would have ignition by. We're in 2017 and it's never happened. Not just at NIF, it's actually in the world it's never happened. But there are a lot of arguments that have come out now where people are saying, well, the reason NIF never worked is because you were validating codes not in the regime where you were actually trying to make the system work. You could never validate your codes at the ignition scale because you never did an ignition experiment. And so it really is an active area of discussion. That is, however, the paradigm that we live in for the weapons. We don't test the weapons, but we do a lot of other things. And we validate codes. This process, this program, is called stockpile stewardship. And so that is the mechanism by which we certify and assess the performance of the U.S. nuclear weapons stockpile without thermonuclear testing. And the language that's up here on the screen is copied straight off of the NNSA website. NNSA is the National Nuclear Security Administration, which is a subgroup of the DOE. So NNSA is called quasi-autonomous, but it lives inside of DOE. And it's a cliche, of course, of me to say this, but that picture looks way better, not on the screen. This, by the way, though, this is sort of one of our classic pictures that we always use. This is one of the things that people in my group actually invented this. It's a probe. It's actually a lens where we just send a laser up from the bottom, and we can basically get out about 300 different directions for that laser by a lens that's in this. And the lens, I mean, it's smaller than that. So, I mean, it's a pretty small thing. And then this thing over here, this is one of our facilities called BEEF, the Big Explosives Experimental Facility, and there we do conventional explosives testing, where we just blow stuff up for fun. And it's really easy when you're driving down the highway on the site. I mean, like I said, the site is like Rhode Island, so we have roads. You're driving down the highway at the site, you know where BEEF is because there's a big sign that is a cow. So it's a cow with an arrow. I'm like, okay, beef is that way. Okay, so in this whole class of experimentation that we're going to do then, so we can't actually go thermonuclear boom, but I want to do a lot of other things to try to test my codes and try to test a lot of fundamental and basic physics about what goes on in an explosion. And in order to do that, we basically built a facility that's 1,000 feet underground in the desert. Actually, I think usually when they report it, it's reported at 963 feet. The urban legend, I have no idea if this is actually true, but the urban legend is if you go more than 1,000 feet underground, then that's a new level of mining regulations. And so we have to make sure that our facility does not go more than 1,000 feet under so that we're not subject to those regulations. So it's 963 feet, not 1,000. But we built this facility and we do dynamic experiments there, dynamic being our word for explosives driven. So we blow stuff up. We don't blow it up in the open, we blow it up in vessels. So we actually will have a containment vessel that's literally about the size that I'm making here with my arms. We blow things up inside and we take measurements. Now taking measurements inside of a containment vessel and blowing things up is a hard problem. And so one of the things that we do is we take pictures of what goes on. Well, if you're going to take a picture, you can't take a visible picture because your visible picture actually is going to look a lot like this, right? You would just see white. So that wouldn't be interesting. But instead what we can do is we can take X-ray pictures. Now if we want to get through really dense materials, you have to use high energy X-rays. So this is not your dentist's X-ray system. Our system, I have pictures. And you really can't see any of this stuff. So I'm sorry about that. That's a little bit better. So there are two X-ray machines. This distance here, the length here of this machine is about 20 feet, and actually here's a slot where they've pulled a piece off that's about another 20 feet. So there's two machines, they're about 40 feet long. They're about as tall as this ceiling, and that's maybe only about 8 feet wide. And so these are definitely not like your doctor's, the machines in your doctor's office. They make 2.25 MeV X-rays, which is high energy, and you don't stand next to this machine when it goes off. That would be really bad. I know this is really hard to see, but just for scale, that's a guy, and he's about 6 feet tall. So a lot of people ask me, okay, you go almost 1,000 feet underground, is it really claustrophobic? And the answer is no. So our tunnels underground, we have 20-foot ceilings. I don't have 20-foot ceilings in my office in the city of Las Vegas. Right, so the actual tunnels that we work in are 20 feet tall. They're usually 20 to 30 feet wide. And then very, very long. We have our total tunnel complex is like 2 miles worth of tunnels. So there's actually nothing claustrophobic about it. You get on this big elevator, which is actually, they just call it a cage. It doesn't really have a top. And you go down, and of course it's pitch black. And you just come out, and you just think, okay, I'm in a big room. That's kind of how it is. And so then we put big equipment like this in there, and you're just underground. We wear hard hats and safety glasses, just being there. Which I never thought, believe me, when I was an undergrad in math, it never occurred to me that I would go to work and put on a hard hat and safety glasses. But it's not bad. And if you want to take pictures of these things then, it turns out there really doesn't exist a decent camera for X-rays. X-rays are very, very hard to actually image because the reason that you use X-rays is because X-rays tend to go through things. So you have a camera, you don't capture the X-rays just go through it. So instead what you do is you have to put up a material that does a good job of absorbing X-rays. And we call these scintillating materials. They absorb X-rays, the molecules in the material get excited, and then they de-excite, and when they de-excite, they emit in the visible. So now I can basically take a picture with my cell phone camera. Now, the camera that we use, the actual CCD itself costs about $250,000. And we have to cool it to minus 60 degrees Celsius. But at the end of the day, it's a CCD technology. It's basically what's in your iPhone. It's just a really expensive one. And you can't buy lenses for that. So we had to invent and build our own lens system. And so we have a lens system. There's actually 13 elements. You can't see those, but it doesn't really matter. But this, all in all, this is about 4 feet and 340 pounds is our lens system. So our lens system alone is that long. And in that cost, I would guess it's about $2.5 million is what it cost us to make that. But I mean, like I said, we had to invent it, so the whole design and development is included in that. We've actually made several more, so obviously the marginal cost of those is less because we already have the design. So this is how our system works. We have these X-rays, we shoot it through a scene. Some of the X-rays are absorbed, some are not. So the X-rays then hit the scintillator, it excites, it gives a visible piece that then we just take a picture of with a CCD camera. And so now we want to use those pictures and we want to make quantitative statements about what was going on inside of the dynamic experiment. Or in some cases, so we do a dynamic experiment a little bit less than once a year. Okay? Now, and when I say an experiment, now I'm talking about an actual dynamic experiment lasts on the outside 40 microseconds. So it's pretty fast, and you do it once a year. But that 40 microseconds costs about $100 million. So even though you only do it once a year, you spend the whole rest of the year tweaking and fine-tuning every aspect of your system. Because boy, when you just hit a 40 microsecond, $100 million button, that thing better work. Right? And so in between our dynamic experiments, we are always taking pictures of static objects. We're always calibrating and characterizing the system. Turns out our X-ray system was designed for a single experiment. So they thought it was going to be fired maybe 100 times total, where they would do like 99 shots of the machine to characterize it, and then they would hit go on one experiment. That experiment was in 2003. We are now 14 years later. It's past the 3,500 shots. It's done about $1,400 million experiments. So now imagine, not only am I trying to maintain this system, but I'm trying to maintain a system that was only designed to be used once. It's actually, I mean, you think about it, it's amazing that 14 years and 14 experiments later, the dang thing still works. Turns out, if you have really, really smart people working on machines, you can actually, I have 6 people whose full-time job is working on that thing. So you can actually keep something running when you have a team that really has to make it work. Okay, so I want to talk a little bit about one of the things that we do. Actually, what I'm going to talk about really for the next 20 minutes is 3 different mathematical problems that we address. The reason I'm going to talk about 3 is because even though the 3 problems are quite a bit different from each other, when we actually get to the mathematical model, you can basically write the same equation on the board and it's going to be the same equation for all of them. And so then when we go to, okay, now I have a model, now I want to develop a statistical formulation, and then I want to develop some actual algorithms, it doesn't matter which of the 3 problems I'm talking about, because I'm really going to get all 3 of those problems into the same model. So it's really nice for us. One of these problems is, I want to reconstruct the density of an object. So one of the things that I really care about when I'm doing a dynamic experiment is understanding what kind of densities the material that I'm blowing up is going through. So in order to deal with that, I do a lot of static experiments, meaning I'm not blowing stuff up, and I try to measure densities from the intensity of the images. Now remember, I'm just pulsing X-rays. X-rays don't tell me density. I mean, and actually it's a CCD camera. When in your cell phone, when you have a picture, what are the units associated with a picture on your phone? And you kind of laugh. That's not a rhetorical question. I mean that. What are the units? Pixels. Well, okay, but in each pixel, you have a value. So what is the units of the value in each of your pixels? Bytes. Actually, I really mean that because I have no idea. I can tell you the word that we use, but it's sort of a fake word. So we talk about the counts in a pixel. So our camera, the one that we happen to use, it measures from 0 to 65,000, right? So wherever that power of 2 is. And so if we get 10,000 is the number in that pixel, then we'll say, okay, we got 10,000 counts. But it doesn't literally mean 10,000 photons. Right? It just means the pixel got excited to the level that we call 10,000 counts. So that's not density. I know what the units of density are. It's not some word that's called counts. Density is grams per centimeter cubed. So how do I get to grams per centimeter cubed from counts? this is actually a really important thing to play out here, because this is actually why I exist. This is why I have a job. Because any physicist can come up with, well, let's take a picture, and I know that X-ray attenuation has something to do with material density, so if I measure attenuation, somehow I'm measuring density. It's that somehow part where now you need a mathematician to actually tell you what somehow means. How do you get to that spot from intensity now to actual volumetric density? And it turns out that basically we can make an assumption. If you have a single material and you have a single wavelength of X-rays, there's a law called Beer's law that says the energy attenuation is just exponential. Okay, fine. What that means is if I take the logarithm of the counts, of the intensity, I basically get something that we would call areal density. Now notice, that's a funny kind of unit for a density. But if you think about X-ray attenuation, it's a function of the density of the material, but also the thickness. So grams per centimeter squared actually kind of makes some sense, because if you take grams per centimeter cubed, which is density units, and you multiply it by length units, you get grams per centimeter squared. And so that's really, just by taking a logarithm, I can almost get myself from intensity to areal density. And then it turns out, once you're in areal density, going from grams per centimeter squared to grams per centimeter cubed is really a tomography problem. It's really a radon transform problem. Well, I'm taking one picture. Actually, if you saw my pictures, I have 2 X-ray systems, but I shoot them at different times, so they each take one picture. So in each of my views, I have exactly one picture. Well, a single projection tomographic reconstruction is what we call the Abel transform, but the problem is an Abel inversion. So it's the radon transform, but now a special case where it's a single projection. Now, the only way that a single projection can actually do you any good in a tomographic reconstruction is if every projection is the same. Right? If every projection is the same, like you imagine X-rays going through your object, well, if it doesn't matter what angle I look at, then if they're all the same, then one of them is good enough, because one has all the information in it. Well, the only way that all the projections are going to be the same is if my object is radially symmetric. And so this is sort of, I would say, I'm going to assume radial symmetry, but I'm going to assume that because I have to actually try to design my experiments that way, because that is the only way a single projection is going to tell me the information that I need. Oh, and by the way, so you're also seeing another a side effect of working for the government. So one of my first side effects here was I couldn't take his USB and put it in my computer. Well, one of the other side effects is I'm not allowed to turn off my screensaver. These are some of those things we just have to live with. Of all the stupid stuff I have to live with, these are pretty minor. So there are others that are much, much worse than that. Okay, so I live in a situation where the actual picture that I'm getting is this data B, and what I want is this density profile U, and this is really a very classical inverse problem. So my left-hand side is the data, and what's inside the integral is what I'm trying to reconstruct. And so this is called a Volterra operator of the first kind. It's a Volterra operator because equations that look like this are Volterra when one of the variables shows up in the integral itself, in the limits of the integral. If this were a fixed limit, this would be what's called a Fredholm operator. And it turns out Volterra and Fredholm operators, they're very closely related, but they also have some really very important distinctions between them. Okay, so that was the first problem. The first problem is I want to take a picture of something and I want to get its density. And I had this mathematical model. It's a linear inverse problem. So my next problem is I want to understand something about the system itself. So now, this is not going to be an experiment that I care about an object. This is an experiment where I care about understanding the machine. And like I said, if when I hit the button it's $100 million, I better make sure that this machine is going to work really well. So I'm going to do a lot of work to make sure that this machine is always operating at a peak performance. One of the things that I care a lot about is, when I think about these images, usually what happens is you have some notional assumption of a plane wave. Well, you can sort of assume a plane wave from a point source if you're very, 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 very far away. If you're far away from a point source, then all of the rays kind of look like a plane wave, meaning they're all kind of coming parallel to each other. Well, I don't have a point source. Actually, it's impossible for any physical system to create an infinitesimally small point source of X-rays. So what I have is a system that's actually going to make a source of X-rays with some kind of extent, some size to it. Now, nothing this big, but usually when we characterize these on our system, it's something like 300 microns. And 300 microns is a lot bigger than infinitesimally small. 300 microns is small, but it's still really big compared to 0. Right? And so, but it turns out that there's a really neat model that says, well, if I want to understand this shape, all I actually have to do is I have to image an object that's just an L. So this is just a piece of metal, and ideally I don't want any of my X-rays to go through that. And then here I've cut out a notch, and there's nothing there, so all the X-rays can go through. Now, those edges are not flat and sharp. They're actually beveled. So that's why we call it a rolled edge, because that bevel is needed to deal with some X-ray scatter. If you have sharp edges on these things, then X-rays scatter badly off the edges, and that'll screw up the information you're trying to get there. So you roll it just a little bit. I mean, this distance here, I mean, we're talking about this being a couple of centimeters, and we basically roll it to a circle whose radius is like 3 meters. Right? So that's a really, really, really small bevel, but it's there, it's real. And of course we call it an L because hopefully everyone can see why we call it an L. But now the idea is, if I want to understand this shape, what I want to know are things like, if the most intensity of the X-rays is coming in the middle, and there's some decay of the X-rays out of the middle, I want to know what that decay is. And I want to know, I talked about radial symmetry before. Well, here, radial symmetry for me is a question. Is this shape radially symmetric, or do I get sort of more X-rays on the top than I do on the bottom? I don't know, that's a question I actually want to answer from this. But if you look here, you can imagine now, this is what my picture looks like. If this were white and this were black, then you would sort of understand. I use color here just to kind of accentuate. But I want to understand like the left-right blurring, and that kind of going from black to yellow is just to demonstrate a blur. It's not a sharp edge. And same thing in the top to bottom. I'm sorry I keep moving so much, I can't help it. This here is also a blur. I want to understand that horizontal and vertical blur, and as you go into that corner, you actually get essentially a full 360 version of what's going on with that blur. It turns out that when we do that, the mathematical model, boy, this is starting to look familiar. This looks almost exactly like the last problem, except the last problem had an extra function in here. If you remember, there was a denominator with a square root. So this one is actually just like the last one, only it's easier. But this, also, the s prime and the t prime actually have my variables s and t, so this is still Volterra because my variables are in the integrals. Now, if you have a double integral, and one's in one variable and one's in the other, actually, like, this is something, you could hand this to an undergrad, and they would come up with something. It wouldn't work, but they could come up with something. Because if you just are trying to, how do you undo an integral? Take a derivative, right? So this would just be take a cross derivative, right? You take an s derivative and then a t derivative and you'd be there. It wouldn't work very well because this is an ill-posed problem, but that actually isn't fundamentally wrong. It's sort of computationally wrong, but not mathematically. But because of that, we actually we'd like to characterize this the same way we will the other problem. Again, we're still just looking at like AU equals B. Well, our undergrads take an entire semester of a course that's just that. So the third problem is actually related to this other one. I want to understand not just the source shape, but I really want to understand the blurring of the entire imaging system. Because that scintillating material that creates the visible light has a blur to it. Our lens system has a blur to it. I'm going to put all of these pieces together. Now in order to do that, in this case, keep coming back to radial symmetry. Radial symmetry was an assumption in an experiment in my first problem. It was a question about the source shape in my second problem. And now in my third problem, we're going to come back to radial symmetry, and it's going to be an assumption I'm going to make. I said I care about whether the blur is the same in all the directions or not. We say, is it isotropic? Well, in this case, I'm going to assume it's isotropic for a moment. If the blur is isotropic, then I only need one line. I only need one edge. Remember, in the L I had two edges because I was asking, is it isotropic? If I assume it's isotropic, I only need one. Because an up-down edge and a left-right edge are exactly the same if I have assumed that it's isotropic. And it turns out in this case, the way that we normally model image blur is as a convolution. Now, when you do a normal convolution, you have to come up with the impulse response of your system. We call it a point spread function, because you're integrating against the kernel. Well, in my problem here, actually, what I want to do is I want to reconstruct the kernel. So I want to know what is the point spread function of my system. Well, if you study convolution, this is the dual problem. But the dual problem of convolution is convolution, which is really nice. Right? I mean, I need some boundary conditions on that to make that a true statement, but more or less that's a true statement. And so what does that mean? It means that, boy, when I actually start to write this down, I start to look like the last couple of problems that I had. This one isn't exactly the same because notice the difference, though my limits of integration now are fixed. I don't have a variable there. Now, because I don't have a variable there, this is not a Volterra problem like the others. This is a Fredholm problem. But those are just names. What's important to know, and this was something I wish people would have told me before I started working with Volterra problems. I've been doing Fredholm problems for 15 years already. But I have only been working with Volterra problems more recently, and nobody told me that they're different from convolution problems because they're better. And ironically, their being better makes them worse. So let me explain what I mean by that. It turns out that research into solving inverse problems like this, so remember my data's on the left, and what's inside my integral, this u, is what I'm trying to get at. That's just a characteristic function, so I know that guy, that's no problem. Solving problems like this goes back at least to Euler. Maybe farther. But at least it goes back to Euler. So people have been studying this for a very, very long time. These problems are what are called severely ill-posed. Now, the easiest way to describe severely ill-posed is to look at it in a discrete sense. Right? When we actually do these numerically, of course, we have to discretize everything, and we program computers to do it. So what you do is you construct a matrix. And if you look at the singular values of that matrix, the singular values of the matrix decay to 0 exponentially. And the exponential part of that decay is what makes this problem we call severely ill-posed. Now, if you look at Volterra problems, those singular values decay to 0, but not exponentially. So they are ill-posed, but not severely. So that seems like it should be good, right? But I can actually draw you a simple picture about why that's bad. So, if you want to know which singular values or which singular vectors, kind of what are the principal components of your problem that matter, and you have singular vectors that look like this, you'd say, well, I don't know, maybe I should cut them off right about there, and this is my interesting information, so be like, okay, I'm going to take the first 10% of the eigenvectors, and then this is all garbage. This is severely opposed. It's kind of not that hard to figure out where to cut. This is not severely ill-posed. Can you tell me where I should cut? I don't know. So somehow this decay is in sort of an on-paper sense and a theorem-proving sense, this decay is better. But in an actual practical sense, when I have to do stuff, this decay is better. So that's kind of fun. But it also, I mean, I say it's fun because, I'm a mathematician, which means I'm a glutton for punishment. And so I only enjoy the problems when they're really hard and I'm not quite sure what to do. Right? Easy problems, when I was a professor, I had a hard time getting my students to understand you should never be proud of yourself for solving a really easy problem. Right? You do something that's really easy and you do it well, you shouldn't get a warm fuzzy from that. When you solve something that's really, really hard, that's when you should be proud. Well, you can't solve something that's really hard if you never work on something that's really hard. So you should want to work on hard problems. In any case, all three of those applications that we just looked at the end of the day, they all just look like this. And so now this is what I want to solve. And in order to do it, I'm going to cast things statistically because now across the DOE for, I would say something now we're getting close to 15 years, we've been moving in this direction where we no longer give answers to any of our questions. We have to give uncertainties. We have to characterize our confidence in answers. So an answer by itself with no notion of uncertainty or confidence is not useful. Well, if you're going to do uncertainty quantification, that sort of means you have to cast things statistically. Or old school deterministic approaches are not really they're not just trying to give us the answers that we need. Now, I come from a background of deterministic inverse problems. I want to cast everything variationally and then write up some optimization problem and solve it. Well, fortunately, I'm not alone in that. And so there's actually this whole community of people coming over from deterministic inverse problems who have moved into statistical modeling, but we all still talk our old language. Which is nice, because do we have statisticians here? Yeah, so you guys know, I mean, the mathematicians and statisticians, we speak different languages, and we're really hard to understand each other sometimes. Or at least, maybe I'm wrong about that, maybe it's only one directional. That mathematicians have trouble understanding statisticians, maybe you guys never have trouble understanding us. But there is a real language barrier. And so it's been nice that we've been able to be a part of this group that's sort of moving from the inverse problems community over into a statistical community where we can actually still relive some of our language. Now, you guys do things statistically, are you guys Bayesians at all? Oh good, then you won't be offended by what I'm going to say. No, the pure Bayesians, so I'm going to show you some Bayesian approaches, but pure Bayesians actually get morally offended at some of the things that I do and say. Coming from an inverse problem standpoint, what I would usually say is, okay, well, if I'm going to solve a problem like this, basically the way that you do it is you actually try to minimize instead something that sort of looks like this. Right? Because if you can make this guy 0, well, this is a norm, so you can make this 0 if and only if you've solved that equation. But it turns out this is actually more flexible than that. And so I want to solve this, or something that looks like it. Well, if I solved exactly that in a statistical framework that corresponds to assuming I have some kind of Gaussian additive noise in my problem. If instead, for example, I wanted to assume I had a Poisson noise process, which actually in our imaging we really like to do, I would use a different likelihood. I wouldn't use that measure. Instead, I would use, right, this is an integral, so instead I would use something like AU minus B log AU, right, D whatever. Right, this is the Poisson likelihood. And so I could use either of these guys as my measure of likelihood, but then these are ill-posed problems, which means you can't just optimize against the likelihood. You have to incorporate some kind of, what in inverse problems we would call regularization. In Bayesian modeling they call it a prior. And that's actually what they get offended about when I say that regularization and prior are, I mean, in my mind they're the same thing. Bayesians get very mad about that. But there's a lot of different things we could do. What I'd like to be able to get at is when I have edges in my data, I'd like to be able to capture edges. When I have smooth transitions in my data, I'd like to be able to have smooth transitions. Now it turns out the way you do these things is by changing your priors, and unfortunately these priors tend to be incompatible with each other. So that if you have jump discontinuities in what you're trying to get at, and you have smooth transitions, you can't do both at the same time. At least not well, with sort of classical approaches. There's actually tons of research still today on how to get both at the same time. But Laplacian, for example, if we use that as our prior, we would get nice smooth transitions. If you use total variation, you get nice jump discontinuities, but they don't do well with each other. And so we actually have an adaptive approach that I'll show. And then once you have a model, right, these two things go together to give me a statistical model. Once I have a model, then I have to actually develop an algorithm to do it. And so in a Bayesian framework, and don't worry, I'm not actually we've already sort of talked through that, but in the Bayesian framework, and I'll come back to this in a second, I just want to show one quick thing here. So none of this stuff actually matters. We don't have to worry about these equations. These equations are up here only because I can say, ha, they exist. And the fact that I can write it out by hand is sort of what matters here. But what I'm doing is, I'm using Bayes' theorem, so I'm just taking my likelihood and I'm multiplying it by my prior to get a posterior. And now uncertainty quantification, what we're doing there is, I want to compute elements on that whole posterior distribution. And if I can characterize the shape of that whole posterior distribution, then I'm going to say that I've done some notion of quantifying the uncertainties. So to get a hierarchical model, what we'll do is we'll make a standard assumption here is something like B is normal. Now, what that means is, that's going to say, okay, what I should do is I should go after my Gaussian likelihood. Like I said, I could do Poisson. Actually, my own personal background is algorithms for Poisson. And actually, I've also done a lot of the classical variational theory for Poisson likelihoods. But it's just easier to show Gaussian. In any case, anything I can do here with Gaussian, I can actually also do with Poisson. And actually, the answers with Poisson come out much more nicely. But if you look at this, then our real big assumption for how we're going to go after our solution is I want to reconstruct this U. Now remember, that was in my first problem, that was density. In my second problem, it was source shape. And in my third problem, it was this blur profile, which is a 1D thing, because remember, I was assuming radial symmetry there. But when I do this, and note my mean is 0, that doesn't make any sense in sort of a theoretical reason. Like, why would I be assuming that my reconstruction would have a 0 mean? And my density certainly is not going to have mean 0. It turns out for all practical purposes, it makes no difference what you put here as a mean. It's computationally completely irrelevant. What really matters here, though, is the covariance, and this thing here. So I have to pick this L, which in a discrete sense, now these bolds are all just meant to be discrete. In a discrete sense now, this is a matrix. So if I were using a Laplacian prior, this would just be the discrete Laplacian. If this were total variation prior, it would be just a linearized version of the total variation, which I mean, we could write that out if we wanted, but I'm not going to. And then this delta here is a scale parameter. In classical inverse problems, this was called a regularization parameter. Now, picking that parameter is actually a big problem. There's a lot of research, I mean, there are hundreds of methods in the literature for how you pick that guy. Only one of the methods, the very first one that was ever produced, that was by Tikhonov, probably, I suppose in the 50s, is called the discrepancy principle. It is mathematically well principled and justified. It also basically assumes that you kind of have to know the answer ahead of time. So it's kind of useless. All the other techniques that exist in the literature, some of the common ones are things like the L curve and U curve and generalized cross-validation. These techniques are all, they're used in practice, but it's actually easy to prove that they are mathematically unprincipled. So I mean, you can show that there are simple examples where they just awesomely break. So what I wanted to do was, well, I don't actually want to try to pick this. I want my data to try to tell me. And if my data is going to try to tell me what that says as well, I should put a prior on that guy and then see if the data can drive it. And so then this is what's called the hierarchical modeling in Bayesian stuff. It's where you take a first level parameter, you put a prior on that, and now you abstract one more level. But I went a step further. I said, you know what? I don't want to pick total variation here, and I don't want to pick the Laplacian, because I don't want to have to completely pick edges or smooth. So what I'm going to do is, I'm actually going to put a prior on the matrix that goes here. Now, I only know one good distribution for matrices, so it was easy to pick what I was going to put on it. Actually, that's sort of a lie, because the Wishart and the inverse Wishart both were, are both these sort of nice distributions for matrices, and it turns out you can prove in hierarchical modeling that it shouldn't matter which one you choose, but computationally we found the inverse Wishart is really much more problematic to work with. I have no idea why. I really don't know. But we worked with the inverse Wishart for a while and then just gave up and we stick with the Wishart. And so now I'm going to do this thing that's actually really quite strange. I'm doing these many, many levels of putting priors on when I use Bayes' rule. Because putting a prior on here is sort of, let's say, done but not commonly. And now putting a prior on here, as far as I'm aware, we're only the second people who ever did this. And the other people who have done this did it very differently. They assumed a diagonal matrix and then they put like a multivariate Gaussian on the diagonal of that. And we just said, well, let's just assume instead that we're just positive definite and go all the way there. Okay, now this is really bad, it would seem, if you're looking, this slide is actually, if you sort of look carefully at it, it's a really terrible slide. And the reason that it's a terrible slide is because if you just took the basic Bayesian model there with my delta, that's one parameter. But now when I put a distribution on delta and I put a distribution also on this lambda up here, just because I can, I'm going to put gamma distributions on those. The reason I pick gammas is because we're going to retain conjugacy among all of these things, but then also gammas can have a lot of different shapes to them. So by picking parameters on a gamma, I can make this sort of relatively flat, just sort of an uninformative prior. So I just replaced two parameters, lambda and delta, with the 4 parameters I need for these two gamma distributions, plus a scale matrix here for my Wishart. This is just a number of degrees of freedom, so actually this, you don't really have to pick this. This can kind of always be the same thing. But now, so I've kind of replaced 2 parameters with 4, which would seem like a really bad idea. The argument that we have here and that we've made is that if you tweak delta by hand, it's very, very sensitive. You really need to have a good idea of what delta needs to be. If you tweak alpha, beta, theta, and phi by hand, it has almost no impact. So those 4 parameters are much less sensitive than the delta parameter. Lambda is actually not sensitive, so lambda wasn't a problem to begin with. Delta is a huge problem. And so our argument is we're going to take that one sensitive parameter delta, I'm going to throw it away by sampling instead, and I'm going to put in 4 parameters that are really insensitive. And in that case, I don't mind having more if they're less sensitive. I don't have to know them. I mean, maybe, I need, and so just to give you guys scales. On alpha and beta, within an order and a half of magnitude, you don't see much change in reconstructions. In delta, a 10% change matters. So 10% versus like 1.5 orders of magnitude is a really big difference. So I don't know what time I was supposed to stop. I'm probably already getting close to the end here. But it turns out we've basically done all the hard work. I'm going to kind of just show pictures now. This is just, like I said, I'm not going to walk through any of this because it doesn't matter, except to say, when I do it with all those priors, I retain conjugacy and everything, which means I could just write out the final Bayes formula, and then I could construct something called a Gibbs sampler, which is the easiest kind of Markov chain Monte Carlo you can do. And Markov chain Monte Carlo is an approach to doing the statistical sampling from a posterior. You construct a Markov chain whose stationary density is the posterior you want to sample from. And so this is just to show, I can actually write this out by hand. And so then if you can write things out by hand, it's not so hard to compute. Okay, so here's results from the density reconstruction problem. So if you remember my cartoon at the beginning, it was these concentric cylinders. And those concentric cylinders, we actually have these objects. They're made out of different materials. And so what I can do is I can look at what is the true density profile, because I know these real answers because I made these cylinders. Turns out this is all simulated, but it's an object. I mean, I could have physically brought it with me. I actually have it, so I didn't just make this thing up. And so 0 density means my cylinders, it's hollow in the middle. So the middle cylinder is literally hollow, so it's 0 density. And then this, man, I think this is rhodium, is our first piece. So that's like 9 grams per centimeter cubed. And then one of these is copper, and one of these is Teflon. So that must be copper, that must be Teflon. And then now you get to the outside again, and you're back to 0. When you actually take the picture, when you look at the intensity, this is a picture you'd get. Because if you think about these cylinders, you think about the thickness and kind of what's going on here as you look through it, you get these sort of shark fin effects in an actual picture. So the real data, the image data, will look like this. So this is clearly not density. But when we took our model and we do a reconstruction without statistics, we get this answer. So the true density profile is dash and our solution is solid. You can see it's not bad, but we missed a little bit here, we missed a little bit here, but it's not too bad.
What is the vertical measurement? What is that? The vertical measurement, the horizontal, I'm sorry, the horizontal.
Oh, I'm sorry. This is just like pixel width.
Oh, just
so I could convert this into millimeters, for example. Yeah, so this is just pixels in my image.
Okay.
In our machine, a pixel is like 34 microns.
Okay.
So if you just multiply this by 34 microns, you get real length distance. But instead of now just using that sort of straight deterministic solution, if we go over to the statistical formulation, where now I'm going to sample from that Wishart and really adjust my prior, now, well, you can maybe see here a little bit better, we nailed down the answer very, very well, and this shading now is just 95% I don't want to say confidence intervals because it's not frequent as confidence intervals. Let's say uncertainty bands that you get from doing 95% quantiles in the posterior. And you can see, where do you get high uncertainty? You get high uncertainty right at the edges, right? Everything kind of spikes at the edges, which is exactly where you would expect to get high uncertainty. So it's really doing the kind of thing that we think it should be doing. But we're really getting the reconstruction very, very well. And so that's just that same picture that was in the lower right. You can see the confidence intervals there a little better. And you can see underneath here a little better too that we're actually really getting that answer correct. So here's the next problem was, remember the spot shape problem is where I had the L rolled edge. And so my data looked like this, where this was my metal, and there was nothing, right? So this is white and black. And then when we do the reconstruction, this is what the shape of my source looks like. This is real data from our machine underground. So this is an actual picture, so these are real pixels. So everything, there's nothing synthetic here. This is just real data. And so that is what my source shape looks like. And so of course we also want to understand things like shot-to-shot variation. Does my source look the same on every time I hit go on the machine? The answer is no. So of course we do a lot of these. And then we characterize that, how does it evolve over time? And actually you can, it's so cliche to say, well, on the computer screen you see it better, but it is really true. but you get an idea, so does that, how do you think I'm going to feel about an assumption in my next problem of radial symmetry? It's interesting, right? Because actually at the highest peak intensities, in the yellow section there on the right, it's actually fairly circular, and the green is fairly circular. It's when you get out to the blue that then any notion of radial symmetry is way out the window. But sort of real at the peak of the spot. We call this the spot. But spot just means radiation source shape. The spot is actually pretty circular in the middle, and then it gets uncircular as you get to the outside. Something that you can't see here at all, but if anybody wants these slides, I can just email them to you, but you really can see in the reconstructions is, well actually I might as well just show another picture. Here's another one. So this is also real data. This is not from my machine 1,000 feet underground. This is from a machine that they used to operate at Sandia in Albuquerque called RITS 6. So this is the Sandians are a team that we work very closely with, and so I wrote a paper with Tim Webb from Sandia on this stuff, and so here's data from their facility. This is also real data. This is an actual image. You note, boy, look at the transition, that left image, compare those two. These are not the same system. Right? I mean, they're really different in their characteristics. But you do notice here, actually, on their spot, it's still, radial symmetry is not bad still at the peak. But you get out, and now, there's a lot more crap going on the outside there. One of the things that also I like to mention here is you sort of see there's these blue spots here. That's actually not coming from real stuff. That's coming from the fact that in this case, because I knew everything was smooth, and I knew that there are no jump discontinuities in this, that I didn't use anything to allow for jumps. So I just used the Laplacian as the prior. I basically said it's a smoothness prior. Well, it turns out that those kind of circle things that pop up out there, those are just eigenvectors of the Laplacian. So that comes from the fact that when I do this statistical sampling, the result is that you tend to over-regularize. So I've imposed too much smoothness on this by allowing my sampler to pick the regularization parameter. By not picking it myself, the statistical method actually said we should do more smoothing. And the reason that things like that happen is that it turns out there is no regularization parameter that works everywhere in this image. In order to damp things down, not get these oscillations here, I have to turn down the smoothing a lot, but then that actually kills stuff up here. And so I really would need a different value here than here. You go into something called spatially varying regularization. If you guys know how to do that and you want to do that, hey, just tell me all the things you come up with because I want to implement it. But I haven't personally done that yet. But that is something, that's sort of the next direction we would want to go. And then just one more picture, and so this is really got long-winded today. I apologize for that. This is also real data. This blue here is, we took a real edge. So I actually just took one of these objects, I took a picture, and we just took a line of pixels across that edge, and now we're looking at it in a log scale. And that blue on the right is actual data. So it's black on the left and it's white on the right, meaning the solid object is, this corresponds to the solid object, this corresponds to there being nothing. Right? And that transition here, that's the blur. If this were a perfect world, it would be 1 and 0. There would be no transition. This isn't the perfect world. It transitions and then you see this is log scale, so this is 10 to the minus 3. Right? So I mean, now you're just in the noise, right? Literally. So what my PhD student Kevin did was he actually developed really a great mathematical theory. He put together, in sort of like a PDE kind of sense, what is the Sobolev space on which you would want to do this reconstruction problem. Because remember, I'm dealing with the blur of a 2D system. I can envision this blur in 2D. And so he had to look at this class of functions where the underlying domain was 2D, but by assuming radial symmetry, you also have to map into the space where they have 1D radial profiles, like on the half-line. So now you have to construct a Sobolev space on the half-line and a Sobolev space on the full 2D plane. And they have to be spaces of functions where you produce an isometry between them that is like this projection onto a radial profile, or going backwards is revolving. And it turns out you actually no such space exists. And so you can't just revolve to go backwards, you have to add in an extra piece. And the reason you have to add in an extra piece is because there exist functions on the plane that are integrable on the plane, whose 1D profiles are not integrable on the half-line. And when I say integral, of course, I really mean square integral. Right? So there are L2 functions of the whole plane that are radially symmetric, whose half profiles on the half-line are not L2 of the half-line. So it's actually really fun. He did some great mathematical theory to construct these spaces and construct them these operators between them that was really good. So the red here is so on the left side is his reconstruction of a radial profile of the point spread. Meaning if I wanted the point spread, I would take that line on the left and I would revolve it. It's thick because he actually has confidence bands there. They're really tight. So you see there's not much going on statistically there. But then what he did was, to test it, he actually took that point spread and he remapped an edge to see, does it look like the data? And so that red is his remapping, and you can see that it almost sits exactly on the data, except in the noise area, right? So it's really a very good reconstruction. Okay, so I'm sorry, like I said, that went very, very long, and I apologize for that, so we'll just stop there. And if you guys have any questions, that top email address is mine. Feel free to email me whenever. I'm happy to share slides and things like that. But thanks for having me.
Do you have a question for Aaron? I may have a statistical kind of question. All the priors you use, they're conjugate priors?
Yes.
They're all conjugate.
And we don't have great reasons for doing that. I mean, the reason is sort of convenience, because I can construct easy MCMC sampling schemes when I do that. We're always looking for better priors. Mm-hmm. But I mean, we have this problem. Whenever you use a Bayesian model, you have to pick your priors. And the sort of philosophical battle here is the correct prior is the answer. And so at what point, where do you decide that your prior is good enough without having to actually know the answer ahead of time? So we're always looking for ways to do that. Like, how can we construct a prior that we can justify, and that seems like it'd be a really, like, mathematically, or really in these cases it'd be really physics that we're trying to use to justify, that would give us a good prior that we'd still be able to construct algorithms for. We've just recently gotten to the point where we've developed some much more flexible Metropolis Hastings. So a lot of Metropolis Hastings algorithms have problems because you have to have these these starting points, but then also your proposal distribution. Sometimes what happens is you get these proposals you can compute, but their acceptance ratio is tiny. So you compute tons and tons of samples that you have to reject all of them. And we're getting to a point now where we actually have constructed some algorithms on problems like this that are starting to work much, much better. We're getting much, much higher acceptance ratios. And so now we can start really going off into these other priors that are really more physics-based and less sort of computational convenience.
So these final results that you showed, they don't change or differ too much if you change your hyperparameters?
The hyperprior parameters do not impact them too much. So let me qualify that just a little bit. So I'm gonna lie, or I just did lie, and I'm gonna tell you the truth now. So there are two sort of things going on there in the density reconstruction. One was if I change the scale matrix that I put into my Wishart. Okay, so the question is, does that matter? And so here's an example. This blue line is what I put into this is the delta I used in the Wishart. So I used the main matrix of the Wishart to be this isn't actually 0, it's a little above 0, but it's just a flat. And yet, if you look at my reconstructions now, they're much noisier, but it went to the right place. It just went there in a very noisy fashion. When I saw this, Mary Lisa did this for me, and I was like, okay, that looks great, I'm really happy, but it still feels a little bit like cheating because my answer has jumps, and here you just took them out. What happens if I give it wrong jumps? Will it fix it? And that was this. So this blue now is a different scale that I sent to the Wishart, where it has wrong jumps. They're in the wrong places. And yet it overcame it. It's still very noisy in the reconstruction, but it's going to the right place. So this was some evidence for us that we felt like this kind of says it doesn't matter that much. I mean, we've given a horrible, horrible Wishart scale matrix, and it's still basically going to the right place. Not as smoothly, but if we would have run this out 5 million more iterations, probably it would. The other thing is the alpha, the beta, the theta, and the phi. You can see, this was not a plant, by the way. These are my only 2 extra slides. So these plots are all plots of different quadruplets of those 4 numbers. Okay, so I just picked different alphas, betas, thetas, and phis. And what you should get out of this is in all of these cases, the actual mean of the posterior was computed almost identically. So changing those did not change the mean that we got to at all.
How about if you choose those such that it's a non-informative prior? Put the same thing there?
Well, so that is, most of these pairings are such that those gamma distributions are pretty much flat. They kind of come up from 0 and just do that. So we try to make them as uninformative as possible, because we don't want our gamma to drive the answer here. But what you will notice if you look at these pictures is those confidence bands are actually significantly different. And that brings up a real philosophical issue for us. Like, can I justify reporting confidence bands when tweaking the parameters still has a significant impact on that? It's a real problem for us. In my life, I actually don't have a choice about reporting things. I live a life where I have to answer people's questions. And I have deadlines that I have to give them answers by. Like, these are not academic exercises for me. People actually make decisions based on what I'm getting here. But in my own group, when we sit and talk about the work that we've done, this slide actually has caused us a lot of pain. And actually, Mary Lisa doesn't like when I show this stuff. But I'm a big believer in. I have a tendency to go around and give talks about all the things I don't know how to do, rather than all of the great things I've solved. But I think that there's a lot of value in that because I like talking to people like you guys who have ideas about this stuff. When you see stuff that you've seen before, if you know what's going on there, I'd love to. Any ideas anybody has, I'd love to hear. This causes me heartburn.
It's not unusual that when you change them, you get different results. That's usually the case.
I think